Imagine a world where computers can solve complex problems in seconds, problems that today's most powerful supercomputers would take billions of years to crack. A world where information can be transmitted instantly across vast distances, secured not by human-made encryption, but by the very laws of physics. That future might be closer than ever, thanks to a groundbreaking discovery by scientists at the University of Oxford. They have successfully teleported logical quantum gates between separate quantum processors, a breakthrough that could reshape the future of computing. In this video, we will break down this incredible breakthrough, explore how it works, why it's so important, and what it means for the future of quantum computing. Quantum teleportation is not about physically moving objects like in science fiction. Instead, it involves transferring information instantaneously from one place to another, using a phenomenon called quantum entanglement. When two quantum particles become entangled, their states are linked no matter how far apart they are. If one particle's state changes, the other changes instantly, as if they were still connected. This is what Einstein famously referred to as spooky action at a distance. What makes Oxford's achievement remarkable is that they did not just teleport a single quantum state. They teleported logical quantum gates, the essential building blocks of quantum algorithms. In traditional computing, logic gates perform operations on bits, the zeros and ones that store and process information. In quantum computing, these operations are performed on quantum bits or qubits, which can exist in multiple states simultaneously due to a property known as superposition. Previously, quantum teleportation had been used to transfer quantum states between physically separated systems. However, the Oxford team went further by using teleportation to create interactions between these distant systems. By carefully controlling these interactions, they successfully performed logical quantum operations between qubits housed in separate quantum processors. This effectively means they wired together distinct quantum processors into a single, fully connected system without needing any direct physical link between them. This discovery directly addresses the scalability challenge in quantum computing. Traditional quantum computers face severe limitations when adding more qubits to a single processor due to increased error rates and decoherence, where quantum information is lost due to environmental noise. The Oxford team's method provides a modular solution. Instead of trying to fit everything into one massive processor, they can now link multiple smaller quantum processors together using teleportation. This allows for much larger and more powerful quantum computers without the constraints of a single chip. Even more impressive, the experiment showed that this teleportation-based approach is feasible with today's technology. This means that practical, large-scale quantum computing might not be as far off as we once thought. The implications of this achievement are vast. First and foremost, it solves the scalability problem, which has been a major roadblock in quantum computing. Most quantum processors today are small and fragile, struggling to maintain coherence when more qubits are added. By using quantum teleportation to link separate processors, scientists can now construct large-scale quantum systems without needing a single monolithic chip. This distributed approach could be the foundation for future quantum supercomputers. Another major implication is the potential for a quantum internet. Today's internet is built on classical communication methods that rely on encryption to secure data. However, encryption can be cracked with enough computational power. A quantum internet, on the other hand, would be fundamentally unhackable because it relies on quantum mechanics rather than mathematical encryption. Since quantum teleportation allows for the instantaneous transfer of information without it ever physically traveling through a medium, eavesdropping would be impossible. Governments, financial institutions, and individuals would all benefit from an unprecedented level of security in communications. Beyond cybersecurity, This breakthrough has the potential to revolutionize multiple industries. In pharmaceuticals, quantum computers could simulate complex molecules, drastically accelerating drug discovery and medical research. In finance, they could optimize risk analysis and trading strategies with unparalleled precision. In artificial intelligence, quantum computing could lead to more advanced and efficient machine learning models. And in climate science, quantum simulations could provide deeper insights into climate patterns and help develop new materials to combat environmental challenges. But perhaps most importantly, Oxford's breakthrough brings us closer to practical quantum computing, where quantum algorithms can outperform classical computers in real-world applications. While quantum supremacy, the point at which a quantum computer outperforms the best classical supercomputers, has been demonstrated in specific cases, this development moves us toward real-world usability, where quantum computers will tackle problems classical machines never could. While this discovery is groundbreaking, there are still challenges ahead. One of the biggest is maintaining quantum coherence. Qubits are extremely delicate and can lose their quantum state easily due to external disturbances. To build large-scale quantum computers, researchers need to develop better error correction techniques and find ways to make qubits more stable. Another challenge is scaling up this method beyond a handful of processors. The Oxford experiment linked a limited number of quantum processors using teleportation, but for a fully functional quantum network, this technique must be extended to global distances. Scientists will need to refine the technology to ensure it works reliably over vast networks. Encouragingly, Oxford's work is not happening in isolation. Other teams around the world are making significant progress in quantum teleportation and quantum networking. Engineers at Northwestern University recently demonstrated quantum teleportation over existing fiber optic internet cables, showing that a quantum internet could be built on top of our current infrastructure. This is crucial for bringing quantum networking into the real world. Meanwhile, Google has been advancing quantum hardware with its 105-qubit Willow processor, capable of performing computations that would take classical supercomputers millions of years. And in China, researchers have successfully teleported quantum states between satellites and Earth, laying the groundwork for a global quantum communication network. These breakthroughs, along with Oxford's achievement, paint a clear picture. Quantum computing is progressing at an unprecedented pace. The world is rapidly moving toward an era where quantum technology will no longer be experimental. It will be integrated into our daily lives. Thank you for watching. If you found this discussion exciting, don't forget to like, share, and subscribe for more updates on cutting-edge technology and groundbreaking discoveries. Stay curious, and see you in the next one.